So yeah, thank you all for joining. I hope you had an amazing lunch. I got to know steak was really good. So I hope you all enjoyed it. And yeah, thank you for coming on a beautiful day. Myself, Dishant Banga. Um, Currently, I'm working as a senior analyst, and today I'm going to talk about one of me and my team published research work, data-driven short-term natural gas demand forecasting with machine learning techniques. So when we say short term, here short term represents hourly basis. Like how does the data demand, how does the use of natural gas demand varies from. Yeah. This is going to be agenda for the day. We're going to talk about why do we need it, about our data, how we procure it, and the models we build. So yeah, short term means as I said refers to the process using machine learning to predict the estimate intermediate or near or future consumption, like as I said, on hourly basis. So lower you'll see typical kind of a flow of how energy is being produced using natural resources and how it was being transferred to the end customer. For it can be customers like you and me, or it can be customers like an industrial person or a residential customer. So so it's really important for local distribution centers to know how much is going to be their future consumption. That is who are the main distributor of our resources, of our energy, to see how much they're going to distribute and what's it going to demand is going to look like. So yeah, that's why we need for energy forecasting to see it's important for both LDCs and their customers, because the actual consumptions sometimes exceeds the forecast. Sometimes we don't need that much energy. Again, that depends upon the so many factors throughout the year and throughout the day. So yeah, before going into data collection, I'm going to share about a little bit about how we procure the data. So those of who are from US, they know Duke Energy is one of the largest electricity supplier in this country. Similarly, in UK, we have Npower. Now they have changed to some different name. So until 2020, they used to organize forecasting challenge. I participated in 2017 and 2018. So this is the data coming from 2018. 2018, they changed the topic to natural gas forecasting. Prior to that, it was journal load forecasting or wind energy, solar energy. So they changed their theme every month. So this topic came out to be a very interesting topic, and it was a different data science, 45 or 50 data scientists from different countries participated, and me and my teams, we secured the top 3 ranks. So this paper is going to discuss about the methodology we used in for that competition, and how we come up with such an accurate forecast. So yeah, some of the data they provided us is the date, block, temperature, wind speed, precipitation, solar radiation, and our dependent variable consumption, which we're going to forecast. And their data was divided into certain time periods, starting from June 2015 to June 2017, about 2 years of data. So we used to forecast every 6 months. So the competition happened in 3 different rounds. Yeah. Other than the given features, we applied some feature engineering based on our research. We come up with some variables like wind chill index, cooling degree days, heating degree days, seasonal effect, recency effect, and of moving average. And our feature, and based on this, we come up with so many variables that for our feature selection, we use sensitivity analysis and principal component analysis to reduce down our features which are feeding into the model so that it doesn't overfit or underfit. And yeah, so we basically developed the 4 forecasting models using different machine learning techniques: ANN, gradient boosting, a combination of PCA and ANN, and a combination of PCA and gradient boosting. So all the 4 models were built throughout the data for the full 24 hours, and broken it down into different blocks. Block 1 represents, like I mentioned, blocks are values from 1 to 4. That data was divided into 4 blocks, 6 hours each. So this is a kind of a flow where we have an input data, our training data, then we build a model, and then the output is our daily forecast, the one which we are predicting. This is a key parameter, key KPI used to measure the success for the model, mean absolute percentage error. It varies from problem statement to problem statement. But yeah, for this problem statement, MAPE was the absolute KPI to measure the success, how good your model is, how accurate your model is. So for different models, we secured like different accuracy, different, MAP values. Like for overall, we scored 13%, somewhere between 30% to 17%, and so on for different blocks. And the final result for the combined models, you can see it's basically we are combining the top two algorithms together in the top three, and how our overall structure looks like by combining all the models. So yeah, based on these, we submitted our results. We came out to be a good forecast. That's why we secured the top three ranks. And our advisor advised us to write a full paper on this one. And you can see this is the blue line is the consumption model, combination model, and the actual demand. So blue line is what we predicted, and the orange line is what was the actual demand. So you can see we are pretty much close to the actual demand, but there are certain points that we're missing that can be due to seasonality, due to consumption, due to a lot of factors. So that's why we have like 10 to 15% of error in our all the models. And yeah, in the conclusion, I'm gonna say it's an important study for our LDCs, for our forecasters to predict the forecast accurately. And for your reference, you can go through the published article which me and my team has worked on. And on behalf of my team, I would like to thank all of you for listening to me. And if you have any questions, I'm happy to answer.